Hello everyone, I'm Dr. Chris. I'm here with my science helper, Max.
Hi.
Today we're going to learn about Newton's laws and some physics by doing experiments and activities. We're going to read a book and we may even watch a video. Now, do you know Newton?
Yeah.
Yeah? What does he look like? Can you see him around here?
It looks like that.
Right there. There's Isaac Newton. Well, he doesn't look like that anymore. Isaac Newton lived over 300 years ago, and he developed many scientific theories that we still use today. As a scientist and a physicist, I still use Newton's laws and the mathematics and physics that he discovered in my daily work. Now, I want to show you an introduction to Isaac Newton. In fact, I met him. Just watch.
It's time to learn about Isaac Newton with Dr. Chris. Isaac Newton was a great scientist. He traveled from the past to meet Dr. Chris.
So Isaac Newton, what are you doing here? What was that machine? Oh, this? Well, this is a vehicle, a car. It uses energy from fuel to transfer energy to the motion. What great scientist came up with this invention? Well, actually, this is all based on your laws of motion. Without your great laws, we would still be riding around in carriages today. Hi, kids. I'm Dr. Chris. Do you know who Isaac Newton is? He was one of the greatest scientists of all time. From today, I'm going to tell you about Isaac Newton's life and the laws that he created.
Isaac
Developed. There were no cars or planes, no electricity or telephone. People traveled on foot or by carriage and used candles for lighting at night. Later on, with many of Newton's discoveries, the world changed a lot. That's why we say Newton is a great scientist, just like a streetlight at night shining on the roads of human development. With Newton's discoveries, scientists have since invented cars, planes, trains, and satellites. I tell you all that I have proven that gravity is universal. It is on this page. Newton was born in a farmer's family, just like many other kids. He was very little. He was so small, he could even fit into a pot. His whole family was quite worried whether he would even live. Nobody could have ever predicted that this little baby would turn into a great scientist who changed the world. Newton lived a bitter childhood. His father passed away 3 months before he was born. When Newton was 3 years old, Newton was raised by his grandparents until he was 11 years old. Before high school, he often got bullied at school, so he would rather play by himself. Doing experiments had become a lifelong hobby for Newton, in which he also found many great science discoveries. Some of his great findings include gravity and Newton's laws of motion.
Let's learn with Dr. Chris.
Very good. So that's the story of Isaac Newton. Now we're going to try to see and feel the laws discovered. So this experiment, you will need a few things. You'll need some flour. We need some balls. So one light and one heavy. Do you want to hold those? And we're going to need some toys. Here we have some dinosaurs, some textures, and paper if you're going to draw some dinosaurs. And then most importantly, a dish where we can hold the flour. So I'm going to put the flour into your dish. And you want to layer about 1 centimeter thick. Does that look good?
Yeah.
1 centimeter. Let's close that up. Let's close that up. So we don't make a mess. It will get messy, won't it?
Yeah.
Okay. Flour. Now we're going to do a test with these different balls. So that means that we need to have a nice flat surface.
Okay.
So we'll try to flatten it out. You can use anything that you have that's laying around that's straight. I have something straight right here. Nice and straight. All right, very good. Nice and straight. Do you want to put some dinosaurs in there?
Yeah.
Make sure you leave room. So we're going to put some dinosaurs in here because our balls, when we drop them into the flour, they're going to make craters. And what happened to the dinosaurs?
They got hit by the meteor.
That's the scientific theory. The best one we have so far is that the dinosaurs went extinct when a meteor hit Earth, and it was traveling slow or fast?
It was traveling fast.
Pretty fast, yeah. Because meteors don't need to be very big to cause a lot of damage, and that's because they have a lot of energy because they're traveling really fast. What about this one? Did you draw that?
Yeah.
What is it?
It's a Brachiosaurus.
Brachiosaurus. What are they known for?
They're long.
Long necks. Okay, let's make some room here for our meteors. Okay, which one do you want to draw?
This.
This one? Okay, I'll drop this one. We'll drop them at the same height. Okay? And do you want to count? And on 3, we'll let go?
1, 2, 3.
Okay, let's have a look. Lift up very carefully. Now, which one made a bigger crater?
More.
Yours, yeah. Look, you see on mine, you just made this little round marking where the ball landed, but yours, it spread some of that flour around.
Mm.
Yeah, because it had more energy.
Yeah. More
Yeah.
mass.
More mass, that's right. Okay, now I'm going to drop it from the same height that you dropped yours, but this time I'm going to give it more speed. Okay, ready? Did you see how the flour went out?
Yeah.
That's because it had more energy this time, because I gave it more speed, right?
Right.
So I think there's some words here that we need to remember. So what was your word?
My word was mass.
Mass. And I want to tell kids about acceleration. Maybe I should figure out how to spell it. Acceleration, okay. Mass and acceleration. And acceleration is changing speed. So you can't see on such small distances, but when we drop the ball, it starts still and then it moves. And it doesn't move the speed that it hits the flour with right away. It slowly speeds up, and that's acceleration. So if we drop our balls at the same time, they'll have the same speed at the top, 0 speed, and at the bottom when they hit. Ready? 1, 2, 3. They landed at the same time. So they landed with the same speed, but yours had more mass. And that's why it caused more damage to these poor dinosaurs.
It's gonna cause even more damage.
More damage? But this one, not so much, right?
Yeah.
So kids, you can try this at home, and you can use different size balls with different mass, and you can tell a little story about the dinosaurs. Maybe it'll be a tragic story like the true story of the dinosaurs, or maybe it will be a more friendly story in which maybe you have a small meteor that's not traveling very fast and they all get to live. Is that good? Do you like that story better?
Yeah.
Yeah. Very good. Okay. Now, would you like to draw your favorite dinosaur? You can explain how you draw your favorite dinosaur using textures there. And we're going to get set up with another experiment. What are you drawing?
A T-Rex.
T-Rex, is that your favorite dinosaur?
Yeah.
And what's the T-Rex known for?
Big T.
Are you drawing it upside down?
No.
Is it hard to draw upside down? Vans, how's it going? Oh, that's pretty good. Excellent. You want to hold it up and show everyone your T-Rex? Half drawn upside down. What? He's got short arms? Is that what the T-Rex is known for?
Yeah.
Big head?
Short arms.
Short arms, big head. T-Rex, long teeth. What kind of dinosaur was it? A carnivore or a herbivore?
A carnivore.
Yeah. What does that mean?
It means it eats meat.
It's other dinosaurs and
dinosaurs.
animals?
Yeah.
Very good. Okay. Let's set that down. Let's move it aside here. Oh, and now we're going to do something a little bit different. Let's make sure everyone can see all of the things we need. So in order to see how acceleration and mass play together, we need to understand Newton's second law. Okay? Maybe we should start with Newton's first law. Do you know Newton's first law?
No.
No. Newton's first law is that things will stay still or continue moving at the same speed unless they're acted on by a force. So these things in front of us, they're just going to sit there and stay still until something comes along and gives it a force. And if you had something that was moving, it would just keep moving until there was a force. That's Newton's first law. Newton's second law is about how forces, mass, and acceleration work. So we're going to build a cannon, a ping pong ball cannon, to show how Newton's second law works and how the force and the mass and the acceleration go together. Okay? Now, force is the most basic concept in Newton's physics. So that one, maybe we should have written down first, because we are using that word all the time, force. Okay, for the momentum cannon, you will need these things. You're going to need some paper towel tubes. And if you don't have paper towel tubes, what you can do is you can take 2 toilet paper roll tubes and tape them together. And then you have something that's the same length as a paper towel tube. We have some paper towel tubes, so we'll just keep those. We have some ping pong balls, and they need to fit inside of your tube. If you have a tube that's too small that doesn't fit a ping pong ball, then you can use another ball, like a bouncy ball, which fits in the tube. Or marble. Or you can just take some paper and crumple it up just so it fits into that tube. Now, we don't want these to roll away, so we're going to set those aside and save them for when we're done building. So you will need 2 of these paper towel tubes. So let's give Max 2. We're going to use some tape. And the most important thing for our cannon will be rubber bands. So we're going to need at least 2 rubber bands each. We're going to use a stapler and some scissors. And we may need a ruler for measuring. Okay, so once you have all of these, then we can start step 1. Okay, so step 1 is to take, if you have 2 that already fit together, then you don't actually need to do step 1. So if one fits nicely into the other one, then you don't need to do step 1. But we'll do step 1 anyway, in case people have the same size tube. Okay, so you have 2 that might fit together. So we'll take the larger one, the one that fits the ping pong ball, and we'll set that aside. And I have one that fits the ping pong ball. Good. So take the larger one, set it aside, take the smaller one, and you're going to cut a straight line down the middle. Straight line. Very good. And you do this to make it just a little bit smaller. So if your tubes were the same size, you make it just a little bit smaller so that it fits in that other tube. Now you need to keep that there, and there are many ways to do that. You just need to fix those 2 together. So we can use stapler, or we can use tape, whatever you have lying around. So you want to use a stapler?
Yeah.
Make sure it's straight. Okay. Maxwell, look, you got to make sure that it's straight. Remember, measure once, no, measure twice, cut once. Is that in the right spot?
Yeah.
Is that where you want it?
Yeah.
You can get more force if you push it at the top. Is that good?
Yeah.
You want to test it to see if it fits? Good. Now I'll do mine. Do you want to help me with mine?
Yeah.
Very good. Test mine. Okay, so you want to Pictures a little bit more? Yeah. Yeah, if it moves smoothly inside, it's much better. So we're going to put our ball in the tube, and this part is going to be the one that pushes the ball out of the tube. So we need to cover the top of that, right? Okay, so now what you need to do is you need to take your tape and you need to cover the top with tape. So 1, 2, 3, maybe 4 pieces of tape that go long enough so they cross the top. Slow down a little bit. It's not a race. Thank you. Is the tape not sticking very well? Well, that's okay. Because then you can go around and you can tape something around the side to hold all the tape down. I can help you with that if you like. We just need something to cover the top. Oh, your tape broke. That's okay, you can use mine. How's it going?
Good.
Good? Almost done?
Almost.
Remember to go slowly, and then you can tape around the outside so that you can hold the tape that you've already put down in place. You want some help with that? Let's get a long one. You hold yours still, and I will tape around. You know, most engineering is fixing problems as you're building. That's the trick. Test, see if it fits. Maybe we need to make sure that you don't have so much tape flying all over the place. Make sure it's a nice circular shape. Maybe you've put too many. Fit through. I think maybe we need to redo yours. If it doesn't slide nicely in and out of the outer part of the cannon, then you won't be able to shoot it very quickly. So you hold the tape down. Oh, are we doing it on the wrong one?
Yeah.
That's not going to work, is it? Okay. Let's do it on the right one. Can you help me by holding the tape down? We'll hold the tape down here. Remember, we want that to fit nicely inside of the outer part. So it can move up and down and push anything out that's already inside. Okay. Very good. Does it fit now? Can you fit it right through the other end?
Maybe this part's too big.
Well, you have to go in like this. That's the way that it's going to go. Okay.
Okay.
Now hold it in there just like that. And what we're going to do is we're going to have an elastic stick to the outer part and to the inner part so that when we pull it back, the elastic will force it to push back in. Okay? So first, we'll staple the rubber band to the outer part. So move the inner part out and make sure that it's as long as the band up there, up high like that. Can you help me? Okay. And we're going to need two. We'll put one on the exact opposite side. Want to do it? Or do you want me to hold it for you? Right up here. Good. You can push the stapler down. There we go. Very good. Is that on the opposite side?
Yeah.
A little bit further. Right there. Good. Okay, so yours looks like this and mine looks like that. And we'll put our second part in. Okay, and then we'll pull it out like that and staple the elastic to the bottom. I'll show you how to do it and then you can do yours. You gonna help? Thank you. Right underneath. Good. Want to help? Yeah. Which part do you want to do? The stapling? This one. 2. Okay. Very good. All right, let's test it out. A ball for you. A ball for me. We place the ball in. And
Wait.
do you know which way to do it? Keep trying. Not so much. Gentle. They're only made of cardboard. Very good. I hope everyone has been able to make their own cannon. Now, there's a way that you can test the cannon. And if you're going to do scientific tests, then you need to do measurements. So to do the measurements, we're going to make some markings on our cannon. Okay? So we're going to make different markings to show the different amount of strength that we're pushing the ball out with. So we can start with the 0 marking, where there's no pull at all. And then we can pull it out a little bit. And we can put another marking. That'll be 1. Oh, I'll have to fix mine. And the 2 marking. And then the 3 marking. And you can make as many as you like before you pull it out. You want to try yours? I'll fix my cannon. So now you have these different markings, and when you do your tests, you want to repeat the test with the same marking each time. Because in scientific experiments, you want to have controls. And those are the things that stay the same in every trial of the experiment. If you change something in the experiment, that's the thing you want to be testing. So if you want to test different levels of pull, then you want that to be the only thing that you change. If you want to change the weight of the ball, then you need to keep the level of the pull the same. You marking yours? Okay, so there's lots of things that you can do to test this. And I have made something here that will be a bit difficult for you to make on your own, so you'll need mom and dad's help. And you can do this afterward. So I'll show you how it's made, and then you can see how we test it, and then you can make it at home. Hold on to that. And you can use this to play a little game as well. So here's what it looks like. It's just a facial tissue box where we've cut the top out a little bit more. And then on the sides, you cut holes. And then you place a piece of paper through the holes. Now I'm going to show you once how to do it by cutting the last hole. So cut a hole in the side. A little bit bigger. And then on the exact opposite side, we need to cut another hole. So this you'll need mom or dad's help with, because you have to poke something sharp through the box. that. We have our piece of paper. We slide it through. Other side. Okay. Slide it through the other side. The third page. And then we need to open up one end. So we're going to open up this end here. One end open, and the other end can stay closed or open, it doesn't matter. So move this out of the way. The paper back through. And this you can use as in a fun little game. So you can think about your cannon as an old ancient cannon, and this as the gates of the castle that you're trying to storm. And you need to find out how much energy, acceleration, mass, force you need to break through the gates. You want to try?
Yeah, let's try.
Okay. If you don't have your gates made, then you can also maybe stack some paper cups as well to see how many of those you can knock over. You want to try the cups or the gates?
The cup. Then the
Cups, then the gates?
I'll try 0
Try 0 first.
first. 1 first. 2. 3.
You have to make sure every time the experiment is the same every time, you're only changing one thing. So the ball has to be inside the cannon, right at the back. And then you can let go. Can you push your finger in to make sure your ball's in the same spot? At level 4?
Level 4.
Yeah. Okay. Very good. Now let's show everyone how the gates work. We have the. Okay, well, we'll look at it from above. That's a good view. You keep knocking down your cups, okay? So we're going. We'll pull our cannon to the same spot. Okay, so I have 1, 2, 3, 4. And we're going to note where the cannon end is being placed because we want to keep that the same every time. My cannonball. Your cannon's much better than mine. And look at this. It's gone through one gate. So you can test that again to make sure it's the same. We've broken down one gate. So Newton's second law says that I can increase the force by increasing the mass that I give it or the acceleration. I can easily increase the acceleration of my ping pong ball by pulling the elastic band back farther, but I can also increase the mass. How far did you get? 2 gates?
And at 7.
Level 7?
The highest one.
That's the highest one? This bouncy ball is much heavier than the ping pong ball. So that should give us more force, right?
Yeah.
And more force will get us through more gates. So we'll try that. And then we'll let the kids test it with all of the different options that they have at home. See? Easy. With more mass, there's more force, and that allowed it to break through more gates. Very good. So kids, if you have your parents send us pictures through the WeChat group that they're involved in, then I can see your cannons and I can comment, and maybe you can ask questions about what might have worked or what didn't work or how you might improve it, and I can see the pictures and comment on them. So while you do that, I'm going to read a story about Newton.
Okay.
All right. Let's just clean this up. Do you want to help clean up?
Yep.
Here. We'll leave our cannons out. I like the cannons. We'll leave those out. Here. Good. Thank you. No, let's keep our cannons. We made those nice cannons. Okay. So this story is called Let's Get Moving. And I'm reading the English translation of this book. So same book, same pictures, English version, Chinese version. Okay, let's set that there. Okay, let's get moving. I'll stand back a bit so you can see too. Or you're gonna watch on the video?
Yeah.
Okay. There's Red Kangaroo. Red Kangaroo's up here actually.
Yeah.
He's been there the whole time. Red Kangaroo loves to play with her ball. When she throws it up, it always comes down. Sometimes it moves fast and sometimes it moves slowly. Red Kangaroo wonders why. Dr. Chris will be able to help me, she says. Red Kangaroo finds Dr. Chris in his lab. Can you tell me what makes things move the way they do? She asks him. Things that move follow 3 rules, Dr. Chris replies. A famous physicist named Sir Isaac Newton discovered these rules. So we call them Newton's laws of motion. I want to know these rules, cries Red Kangaroo. Can you please teach them to me, Dr. Chris? Yes, but first I need to teach you 3 very important words that will help you understand Newton's laws. They are force, mass, and acceleration. So these are the words that we wrote on our board up here. Force, mass, and acceleration. Let's start with force, says Dr. Chris. Force is any push or pull on something. An example of this is pushing a door open or pulling it shut. Push. And pull. Yeah. So we learn about force and we see force every day. So I'm using force when I throw my ball into the air. My force pushes it up, Red Kangaroo asks. Exactly. And gravity is the force that pulls it back down. Dr. Chris responds, gravity is a very important pulling force. Without gravity, everything would stay up in the air. Next, we have mass, Dr. Chris continues. Mass is how much matter something is made of. I get it. The bigger the ball, the more the mass. Red Kangaroo says, yes, very good, says Dr. Chris. And we can connect mass to force. Let's throw both balls in the air. The ball with the greater mass will feel more force of gravity. So who feels more force of gravity, me or you? Yeah. Finally, we have acceleration. This is change in speed, says Dr. Chris. A ball is accelerating if it starts out moving slowly and then goes faster. So the balls that we dropped into the flower that created the craters, they started without moving, and then by the time they hit, they were moving quickly.
Yeah.
And they would keep moving quicker and quicker and quicker if we allowed it to keep falling. That's acceleration, changing. And also when the ball stopped, that's acceleration as well. Sometimes it's called deceleration, but it's all acceleration. Anything that changes its motion is acceleration. I understand force, mass, and acceleration, says Red Kangaroo. Am I ready to learn Newton's laws now? Yes, you are. Let's go back to the lab, replies Dr. Chris. Newton's first law says that an object will either stay still or continue moving at the same speed and in the same direction unless a force acts on it. So something will just keep moving at the very same speed until there's a force. Something that might stop it or something that might change its direction. Otherwise, it just keeps moving. That's Newton's first law. So this ball is not moving and will stay that way unless I push it, asked Red Kangaroo. Yes, when you push the ball, you use your force to make it move, says Dr. Chris. The ball will continue to move at the same speed until my hand or another force, like the wall, stops it. Now, let's move on to Newton's second law. This law says that an object with a greater mass will need more force to accelerate it. So the more mass, the more effort you need to get it started. Can you think of any examples where that's happened to you? I don't mean in the room now. Maybe in the past? Heavy door? Maybe a heavy door or, yeah. Yeah. A heavier door needs more force to get it to move, yeah? Yeah. And that's why big trucks in the road start slowing down much sooner than everyone else or take longer to get going at their top speed. Okay. I push both of these balls with the same amount of force, says Red Kangaroo. Does Newton's second law mean the smaller ball will accelerate faster because it has less mass? You've got it, Red Kangaroo, Dr. Chris replies. But you can also have them accelerate at the same speed. You would just need to use more force on the bigger ball. We have just one law left. Newton's third law says that for every force that acts on an object, there's an equal force acting in the opposite direction. So for every force, there's an equal force acting in the opposite direction. There's always two forces, never one force alone. There's always two. When I push on you, Dr. Chris, I can feel you pushing back on me, Red Kangaroo says. Exactly, says Dr. Chris. And you feel the weight of your ball pushing back on your hand when you push it or throw it in the air. You want to see a good example of that? I'm going to hold my hand still. You give me a high five. Now, you may have thought you were hitting my hand, so my hand should maybe feel a slap. Maybe it should hurt. But your hand will feel the exact same force. Try it again. You feel it on your hand? That's Newton's third law. Thanks for teaching me the rules of motion, Dr. Chris, says Red Kangaroo. Now I can think just like Newton and see his three laws of motion wherever I see something moving. That's the end. Okay, so I think we have some pictures I can see that you've sent of your cannons. Okay, the first one. This is Derek. Very good. Oh, that looks great. Look at that. Excellent work, Derek. And who's this? This is James? James, and he's got his name written on there. Very good. Excellent work, James. And Kim, it's a small cannon with a golf ball. That one would have a lot of force. Yeah. And Vivian? Yeah. That one looks very good. And Chloe, oh, she's decorated hers. Excellent work, Chloe. Erica, oh, that's a very good cannon. Look at that. And they have the gates as well.
Yeah.
And look at all the levels. That's going to make for some good scientific discoveries, I think.
Yeah.
Okay. Excellent work, Erica. Now we have Raymond. Oh, that's a great cannon. Oh, and he's got his, yeah. And who, we on Bianca? Ah, very good, Bianca. And she's doing the test with the gates. Very good. Nathan? Ah, he's got his skates. Very nice. It's an excellent cannon, Nathan. And Vincent? Look at that. That looks huge. Look at his cannon. Excellent work, Vincent. And it looks like last we have Michael. Ah, look at the very carefully and perfectly spaced levels
Yeah.
for the measurements. Very good, Michael. Oh, that's great work, everyone. Those look wonderful. I hope you're able to see how you might be able to test these at home, and maybe you can see Newton's second law in action. Okay. All right. So now we're going to do one last experiment. So we'll set our cannons aside, and we're going to see Newton's third law in action. Okay, so for Newton's third law, we need some string and some tape, tissue box, scissors. So I'll give you some as well. Are you going to do one as well? Yeah, you want to do one as well? This one's tricky. So we need some ping pong balls. You have some ping pong balls. Okay, let's keep the ping pong balls in there. Otherwise, they roll away, and then we lose them all. Okay, so we need scissors, tape, a tissue paper box, empty tissue paper box. You don't want a full one, empty one, and some string. Okay. The first step is you're going to cut the side. We'll cut a hole open in the side. Do you want me to get it started for you?
Yeah.
Yeah, let me get it started for you, and then you can cut. So to get it started, you just want to poke a hole with something sharp. There you go. Now just cut a square out. And remember, it's not a race.
You mean a rectangle?
A rectangle, that's right. I mean a rectangle. It's a good thing you're here to correct me. Rectangle out. Okay. Rectangle cut out. And that's for viewing what's going to happen inside. Yeah, very good. And the second step is to cut another rectangle out of the top. And make sure when you cut this one out, you don't get too close to the edge, okay? Because this edge here has to stay nice and sturdy. Okay, so don't get too close to the edge. So we'll cut another rectangle out. You got it? What's up? No, just start here. Just start here in the middle. There you go. See? See how I just started in the middle and went towards the side? You're going to cut the plastic out first? Oh, there you go. Tough, isn't it?
Yeah.
Cut holes and things. Can be difficult. You're doing great. Great job. Just be careful not to break the box. Try from this side. Try this way. You can wind right to the end. Good work. Okay, so if you have a part that's not quite steady, you can first, before we get started, just fix that up. So piece of tape there. Just fix that up because we don't want that to break. Okay. So now we want several pieces of string that will fit across the top and hold a ping pong ball down at the bottom. So they need to be about twice as long as the hole. Okay, so I'm going to cut some string. 1, 2, and 3. I can help you. Would you like me to hold the string, or do you want to do the cutting?
I want to do the cut.
Okay.
So here.
Yep, right there. 1, 2, and excellent. We need to tape some ping pong balls to our string. And this you definitely need help with because it has to be very carefully placed. So I am going to hold the string and the ping pong ball, and you put a small piece of tape just right across there. Okay, nice and tight. And it's going to hang right down in our box. Good. Right in the center. So it hangs nice and simple in the center. Good. Second ping pong ball. Tape it right in the middle. Wait, let me get it lined up. Yes, very good. Now this is the trickiest part. You want it to be just touching that ball and at the same height. Now if you do it exactly like this, you can change it by just pulling the string, because the string will move inside or underneath the tape. So you don't have to get it perfect the first time. Just gently pull the string, it'll move inside the tape. Okay, and the last one. Hold on. There we go. 1, 2, 3, and let's make sure it's straight. There we go. Okay, I can help you with yours. Let's just do two balls on yours, and then we can see the difference between when you have 2 and 3 balls. So let's get a ping pong ball. Also, we only have 2 ping pong balls. So that works out perfectly. Very good. It's great teamwork, isn't it? Yeah. Okay, now they're done. Do you know what these are called?
I forgot.
This is called Newton's cradle. Or that's a Newton's cradle and that's a Newton's cradle. How would you make it work? What can you do?
You push that back and then
And what about this one?
push that back, and then that one moves. It
Oh.
passes through that one.
Yeah.
And they just start to go up.
Well, what
crazy.
will happen if I happen if I move 2 at a time?
Then both of them will give that lots of force.
Yeah. You think so?
Yeah.
And it's a bit hard to see. And it's very tricky with ping pong balls because they you can hear them, right? When you can hear them when they move and they shake the wire. So there's lots of friction happening and lots of energy is lost very quickly. But you can get from a toy store a better Newton's cradle. And you can try the 2. You see that? So again, as you pointed out, the middle ones should stay still while the other 2 move. Now pull 3. See what happens. You see, the 3 didn't just hit the 2 and knock it away.
The one in the middle.
The one in the middle went with it, didn't it?
Yeah, and then it went like that, and then it just kept.
Yeah. Lots of Newton's third law action happening here. So for every force, there's an equal force in the opposite direction. And the original force was this ball hitting here. And then the energy was transferred all the way out to this ball. And then eventually we're going to see that ball get knocked all the way back.
Oh, is mine better?
Now there's lots of other things being demonstrated here in Newton's cradle that we haven't talked about. So Newton's laws aren't just those 3 simple things and that's it. They teach us all sorts of other things that you might be able to see inside of Newton's cradle, like conservation of energy and momentum. You can play with all sorts of different things. What about you pull one up on your side and I pull one up on my side?
Ready, set, go.
Look at that.
And that one just stays there because it transfers the energy to the other one.
Yes, very good. Well, I hope that you were able to make a Newton's cradle yourself with just ping pong balls. And I challenge you to maybe make one with even more ping pong balls, or if you have some metal balls, or you can use something like a marble, and that will give you a much better Newton's cradle than with the ping pong balls. So thank you everyone for listening. We have time for some questions, and for everyone who asked a question, then I will sign a book and send it to you. So do we have any questions? Will Newton's cradle from the shop ever stop? That's a great question. So the cradle that you built does stop, and it stops very quickly.
Yeah.
And that's because of all of the friction and all of the lost energy. The cradle from the shop will, so if we let it go and just watch it, it also loses energy as well. And you can see it will slow down and slow down. And eventually, yes, it will stop. But the better it's made, the longer the bouncing will happen for. And you can see that you're losing some energy when the whole thing is kind of moving back and forth. And that's what happens to your ping pong balls. If you can build a cradle that is very, very rigid, very, very tough and hard, and has made of very, very solid things, then it might last a long time. But all cradles will eventually stop. You've made a great one. Thanks for your question, Mitchell. And this is a book for you. Okay, if you have any more questions, then you can send them in our WeChat group. So that's it for now. Are you ready to say goodbye, or are you having too much fun with that cradle?
I'm ready to say goodbye.
Thanks, everyone.